This lesson is on optimization. The objective is, how do you use calculus to determine the absolute maximum and minimum values? In most cases, optimization is going to be used in solving various types of word problems. Now, there's certain guidelines or steps that you need to follow as you would with any mathematical word problem. The first of these guidelines is to identify all given quantities and all quantities to be determined. In other words, what do we know and what are we looking for? And if it is at all possible, try making a sketch, okay? You do not have to be a beautiful artist or anything like that. A crude sketch can often help you immeasurably. The second thing is to write a primary equation for the quantity that is to be maximized or minimized, okay? So here we're looking for an equation, basically. An equation that identifies what are we looking for that we want to find either the maximum or the minimum. The next step is to reduce the primary equation to one having a single independent variable. Okay, that's very important here. This may involve the use of secondary equations relating the independent variables of the primary equation. So in other words, if we have something like the area is equal to the length times the width, somehow you have to equate length and width so that there's only one variable there, that you don't have two variables. The next step is to determine the feasible domain of the primary equation. That is, determine if the values for which the stated problem make sense, okay? In some cases, you may actually be given a domain, a limit, from this value to this value. In other cases, you may end up with an answer, and in one case, it may not make sense. For example, if you're looking for maximizing a length, and you come up with a negative value, this doesn't make sense. There's no such thing as a negative value. Similarly, if you're asking for maximum area or maximum volume, and you come up with negative or beyond the range of what you're given, then that also does not make sense. So it's very important that you look to make sure that the result you get makes sense. And then lastly, determine the desired maximum or minimum values by calculus techniques. And these are first derivative tests, second derivative tests, things like this. Now, I know this lesson is referred to as optimization, but in reality what it is are max-min problems, and they pretty much fall into three different categories. The first is abstract functions, and these are cases where you're given a particular function and you're asked to find either the absolute max or the absolute min over a certain range. Okay, the second and probably the most common variety are geometric. So these are problems involving volume, area, things like that. Finding the maximum size for a box given a certain amount of material, or the maximum area or the minimum area, things like that. And then the third involve rates. So these are the three basic types of categories that these optimization problems fall into. So let's look at an example of an abstract function type problem. So this would be a case where you're given a particular function and you're asked to find the absolute max and min for the following function, okay? And what's important here is we are given a range, okay? So we're given a range over which we are looking for this max and min. So the first step is we're going to simply take the derivative of this function. So we got a function x cubed minus 6x squared plus 9x minus 4. If we take the first derivative, we're going to end up with 3x squared minus 12x plus 9. All right? Now, we can obviously simplify this by factoring out a 3, and then we can factor the x squared minus 4x plus 3, and we end up with, in simplified version, the first derivative is equal to this, 3 times x minus 3 times x minus 1. So this, what does this tell us? Okay, first of all, it tells us we have some potential turning points, okay? We have potential turning points at x equals 1 and x equals 3. However, we got to remember up here, we were given a particular range. So we have two other points of interest, and that is we have 1/2 and 5 to consider. So we really have 4 points of interest. We got 1/2, we got 1, we got 3, and we got 5. So what we're going to do now is look at this and plug in these values. So we'll take 1/2, plug it back in the original function and see what we get for y. We'll take 1, plug that back in the original function and see what we get for y. We'll take 3, plug that back in the original function and see what we get. Take 5, plug that back in and see what we get. And notice these are the results we get. So for 1/2 it's minus 7/8, for 1 it's 0, for 3 it's minus 4, and for 5 it's 16. So obviously, in terms of what the absolute minimum is, the absolute minimum is this right here, is the minus 4. So the absolute minimum is minus 4, and that occurs at x minus 3, because minus 4 is obviously the lowest of the 4 values. But the absolute maximum now, as you can see, is 16. So the absolute maximum occurs at x equals 5. So here's a typical example of how we take and find absolute maximum and minimum of an abstract function. The next example is the one that you'll probably see most of to fall into this category, and that is geometric type problems, okay? So here's a particular example. We have Mr. Kelly. He needs to make an open top box to store all his magic cards. He has a piece of cardboard that is 14 by 30 inches. To do this, Mr. Kelly cuts out squares of equal size from the 4 corners so that the 4 sides can be bent upwards. What sizes should the squares be in order to create a box with the largest possible volume? Well, first of all, we've created a picture here, all right? And we have a rectangle. We know it's 30 by 14. And we know that each of the corners is going to be a square that's x by x, okay? So he's going to cut 4 squares out of the corners, and then he's going to fold the sides up to create an open top box. And we want to know what size must these corners be in order to create a box with the largest possible volume. Well, it's obvious that volume is simply equal to length times width times height. Well, we've got too many variables there, so I've got to equate all of these to one thing. So the length of the box is going to be what? Well, it's no longer 30 because we're going to cut 2 squares off. Each square is x, so it's going to be 30 minus 2x. The width is going to not be 14 anymore. It's going to be 14 minus 2x. And the height is going to be x. So if we multiply this out, we'll get 420x minus 88x squared plus 4x cubed. Well, kind of an ugly looking cubic, but if we take the derivative of that, we end up with 420 minus 176x plus 12x squared. Now, you set that equal to 0 to find out the critical points here, and you simplify it, and we end up with this, 3x squared minus 44x plus 105 is equal to 0. If you factor it, now this might be ugly to factor, but you can do this on your calculator to find out factors, and we come out with 2 answers, as you'd expect. X equals 3, and x equals 11 2/3. Well, x equals 11 2/3 doesn't make sense because the box is 14 inches wide, so each of the squares cannot be 11 inches. So that would make it 22 inches, which doesn't agree with what the given information was. So obviously our answer therefore is x equals 3, and therefore each of the boxes has to be 3 inches on a side. So they cut out 4 corners, 3 inches on a side, and that will give us the maximum volume box that can be created from this sheet of cardboard.